Hi and welcome to another edition of Ordinary Differential Equations. Today we are going to talk about step functions. Let's go ahead, take a look at this and see what this topic is all about. Okay, step function is a particularly simple function with a rather peculiar look. If we have our axes as in the standard position, and this is the time axis, and this is some function, let's call it u, and that function that you are considering is staying at 0 until a certain time c, at which it abruptly changes to a function with a height of 1. We call this thing step function. So it's switching from 0 to 1. And we write this thing as u sub c of t, or at least your textbook writes it this way. So this is a function that is piecewise defined in a very simple way. It is 0 if time t is less than c, and it is 1 if time t is larger than c. At time c itself, you can think about the value of the function to be anything you wish, either 0 or 1. That's not going to be all that relevant to us. It's a rather peculiar function to have an entire section devoted to itself, but you can sense that it's very important because it resembles the action of a switch, meaning if you have a light switch that is in off position, and at a certain time you decide to turn on the light, then the function that's going to model that kind of a behavior will look like this. So this is during the time where the light is off, and this is the time at which during which the light is on, and C is the time at which you turn the switch on. Well, many appliances have switches. The simplest one is your light switch, but internally many appliances do have their own switches and circuit boards and such. If you want to visualize a mechanical system that has a switch to it, we can go back to our spring system. Imagine we have the spring, and to this spring we attach a pan, and at various times you might decide to add a certain weight to this pan, or perhaps take a weight off of the pan. So the addition or removal of the weights while this thing is oscillating is going to cause a rather complicated behavior for the system. So the addition and subtraction of these weights will be a switch for this mechanical system. We are having the following perspective, that we want to solve differential equations as before, with the setup as in forced oscillations, where we had the mass times the acceleration plus some constant of drag times velocity plus spring constant times position, and that was equal to the external force. Now the external force that we have in mind, this external force will be of this variety, that's going to have step functions in it, and is going to change abruptly from one value to another value. Very standard problem that comes up in circuits. So you can imagine that we need to know what is the Laplace transform of a step function, and then we are going to gradually add more and more complication to this so that it will resemble systems that you are going to encounter later on. So let's go ahead and see how we handle a plain and simple Laplace transform of such a basic function itself, and then we'll have more problems to consider. So What is the Laplace transform of the step function? Well, in the previous lectures we have seen several problems resembling this. We just didn't call it a step function. We said that whenever you have a piecewise defined function, you take your integral and split it according to critical times that you have here and just do the integration. So that's what we are going to do here as well. So I have by definition I have to integrate from 0 to infinity of exponential of minus st times my function. Well, we said we take this integral, break it according to our time. So we go from 0 to c exponential of minus st uc of t dt, and then we go from c to infinity of the same thing, exponential of minus st uc of t dt. So at the beginning the light is off, this is 0, so we are lucky that there's nothing to be done here, it's just 0. And later on it's simply 1, so it goes from c to infinity of exponential of minus st. My function is just 1. And when I integrate this thing, well, it becomes exponential of minus st over minus s from time c to time infinity. At infinity, as usual, we have the same discussion what is going to happen at infinity, and then minus sc divided by minus s. So for a positive s, this is going to be 0, so we need to assume s to be positive for this thing to make sense. This is going to be 0 minus exponential of minus sc over minus s, and out comes minus exponential of minus sc over minus s. So we have one new fundamental formula added to our table. So I'm going to write it, Laplace transform of step function is excuse me, I made a mistake here, and the minus evaporated. So we have exponential of minus sc over s. Well, let's go ahead, practice some basic things here, and then enter this thing in our big table, and then start working on some more advanced example. Let's ask the following question: what is the Laplace transform of say 3 of t? It simply means the light is being turned on at time 3. So it's simply exponential of minus 3s over s, so that c becomes 3. More often than not, more important thing is to go backward. What is the inverse Laplace transform of, say, 5 exponential of minus 8s over s? Well, 5 is just a multiple, and this is Laplace, the step function at the critical time 8. What does this mean? At time 8 seconds, we have a voltage of 5 being turned on, and prior to that it is simply 0. And of course we still have the linearity as before, so we can have multiple switches in our system. Let me make it straightforward. So I can have, for example, 5 u2 of t plus 7 u3 of t. As you remember, when you have addition in multiplication by numbers, this just splits across the functions that you had in the most trivial way. So 5, this becomes exponential of minus 2s over s, and 7 exponential of minus 3s over s, and vice versa. Going from this back to that will be just as simple. Now we need to understand, well, what does this function really represent? That is what's going to prepare us a little bit for the circuit courses and such. What is this thing? So uh, so many problems you see in this section is asking you the detail of the functions we are considering a lot more than just the Laplace transform of it. So I might ask, what's the graph of f of t is equal to, say, 5u of 2 of t, and let me make this a little bit different, maybe 4u 6 of t. So what is this? Well, smart thing to do is to indicate times that we are concerned about on the horizontal axis. So say this is 2, so 4, and then 6. So smallest time at which something happens is 2 seconds. Before that there's nothing. So before that we have that 0 voltage, nothing is there. At 2 seconds, u sub 2 of t becomes 1. When you multiply it by 5, well, that means you're going up to, say, voltage 5, or whatever 5 means for you. For a while it's going to go on like that. That is as still not effective because its critical time has not arrived. That's still at the 0 stage. At time 6 you open the gate to this. At time 6, so up to time 6 we are just going to go with voltage 5. At time 6 we have an additional current coming into the system whose voltage is, say, 4, and that's going to add on top of what we had before. So if we go up by 4, and then after that there are no switches, so that's where you stay. Well, you gradually get a sense why this is called a step function. Well, because it looks like a step. The more of these things you have, the more steps you have to go up. And unlike building steps, you can have a subtraction, in which case you come down. You could go up a few steps and come down a few steps, resembling some of the exercise setups. So sometimes the graph is given and then you're asked to actually produce the function. Again, you look at your graph, see what are the critical times. Those are where the C's are going to be at, so at 2 and 6. And suppose on the graph we see a voltage of, say, 5, and later on a voltage of, say, this is 9. So 5 is my first coefficient or multiple. 9 minus 5, that is 4. That's the coefficient of the next function. So 9 minus 5 equal to 4. So the new height that we are going up with or coming down with, those are going to be the coefficients of the functions as we write them. Okay, so this was some basic ideas about the step function, and now on to the next interesting fact. Well, many times you're not just interested in a flat function starting at a certain time. Rather, you have say a sinusoidal wave or some sophisticated wave starting. So the look of this step function is very simple. It's assuming at time c you're just interested in a voltage that's a flat 1. Well, of course, you know there are lots of voltages out there that are not direct currents. They're like alternating. So you don't start a flat event. Rather, you start something that has some waves or some flavor to it. So what we want to do is to take all those functions that we had worked with before and assume that we want to turn a switch and start a wave or start a voltage at, say, sine of 2t, cosine of 2t, exponential of minus 3t, or whatever function you have in mind. So the question is, how do we handle that? So suppose there is a function f of t, any of those sine, cosine, exponential, whatever that you had before, and you already know what is its Laplace transform. Any of those functions we have practiced before. Now what we want to show is that if you take this function, delay it by 3 seconds and turn it on at that moment, what would be its Laplace transform? So what we are after is the following. We take this function, delay it by 3 seconds. That's how we write the delay of a function, f of t minus c. In college algebra, you recognize this thing as shifting the graph of a function. So we are shifting the function 3 seconds to the right, and then we are going to turn it on at that moment. And then we are going to talk about what would be the Laplace transform of this thing. We are going to show two things. One is that, well, Laplace transform is going to be very simple. It's going to be exponential of minus cs times f of s. The formula itself is very simple, but to understand what is involved here, that's the really crucial issue. So let me start doing a tiny review of some basic ideas from college algebra, where this type of an expression shows up quite often, and then we will have a better understanding of this picture. So if you allow me, I just do open a parenthesis here and do a tiny review Okay, so in an algebra class, you start with perhaps the most familiar function, say y equal to x squared, is that right? Our trusty parabola. Here's our graph of this parabola. Okay. Now suppose in this parabola is a piece of cardboard or wire or something. I want to take it and move it around. Best way to describe it is as to where do you want to put this thing. Suppose I want to put it, say, at location 5, that I have brought this thing here. So this black one is x squared. The question is, what is the formula for the red one? Let me pause for a second and ask you guys, be sure of your answer. There are probably 4 choices that come to your mind as to how does that number 5 show up in the formula, and try to seriously convince yourself which one of them is the correct one. That's going to be very crucial for us, and then let me know. So what is the formula for the red one? If you set x minus 5 squared, you are the grand prize winner. You are remembering the idea from algebra. One of the easiest way to see that subtracting a quantity from x pushes your function to the right is just set this thing equal to 0. Remember the formula, set it equal to 0. The root of it is at 5, meaning from the root of this thing that was at 0, you have moved to the right by 5 units. So subtracting from x has the effect of moving to the right by that much. So this is referred to as a shifting or translations of functions. Now what we have in mind is not only take a function and move it to certain future time, rather we are going to be truncating it, that is erasing the left hand side and just keeping the right hand side of it. That is, what we have in mind is keep everything dormant until 5 seconds and then turning on this parabola. So we are getting rid of the left side of this function. We are truncating it or doing a little bit of a surgery or something. So going right by 5 seconds, that is the delay portion. taking the function f and delayed by a certain number of seconds. But that by itself still drags the left side of this function alongside with it, and typically that's not what we want to have. We want to be at 0 and then just have the right side of this function. How do we do that? Well, we multiply our function with a switch. That switch makes sure everything is 0 up to that time. After that critical time, it becomes 1. So when you multiply 1 by whatever function you have, well, you just get that function back. So the net effect of having this switch here is to turn everything off and keep it at 0 before that. So that's the meaning of this. Instead of a parabola here, we could have a sine, cosine, exponential, whatever you want to have. That doesn't make any difference to the discussion that we had here. So you're going to hear me often talk about the switch and delay activity. Remember what we just talked about. We have the switch and we have the delay. And a very crucial thing in problems that we are going to look at later on, and a little bit of a mathematical twist to this, is to be careful that these two indicators are the same thing. That is, your switch should match your delay, otherwise you have to go through some fancy footsteps to get the answers right. Okay, before we actually show where does this formula come from, let me just go ahead and do some problems to make sure everybody understand what the formula really means. So let me remind you, say, of what was the Laplace transform of cosine of, say, 3t. Okay, in 1 second. What was it? You have to be very fast with this thing to be ready for your next circuit classes and such. So you shouldn't rely on that table all that much. You have to kind of look at that table so often that it becomes second nature to you. So you remember that this was s over s squared plus 3 squared, right? Now suppose I don't want cosine of 3t, rather I want it to come into the play 11 seconds later. So I'm going to have u11 of t, that is to keep everything off at 0 stage up to 11 seconds, and then cosine of, now again I'm going to pause this thing and you tell me what is it I'm supposed to write in the parentheses here. How do I push this thing 11 seconds to the right? Exactly what would I write? Again, there are two choices. Make sure you make the right choice. It's 3 times t minus 11. Not to be confused with 3t minus 11, which is an entirely different story. It's a t that is replaced by t minus 11. What happens to, question, what happens to my Laplace transform? So what happens is that this has been pushed to the right, and the net effect is that exponential of minus 11s times whatever you had. So the formula is quite simple. It's we are multiplying by this function exponential of minus cs. Now let's go ahead and practice something else. Let me see if we can ask everybody to figure out what is the inverse Laplace transform of exponential of minus 6s over s, say, plus 7. Okay, take maybe 2 minutes, maybe even more, to be absolutely sure of what your answer is in this case. what should we say? Okay, there are some standard mistakes students make in which is sorry uh, the formula looks simple, but the errors are quite common. So let's see, what do we do? In the formula itself, you see that we have the original Laplace transform intact. So we can put aside the exponential, take the rest of it, and figure out what is the inverse Laplace transform of that. That's going to be your little f of t. Then, crucial thing to remember is that you are shifting that. Students usually forget that component, that you have to take that thing and shift it back. Let's see how does this go in this case. So again, let me just it's the best thing that you discover it for yourself, and then you come back and continue. Okay, so I strongly recommend that you do this, because everything we do from here on this topic relies on this critical issue. So we do like this. We say, okay, let's ignore that exponential for a second. If I just had 1 over s plus 7, what would have been the Laplace transform of that? What is the Laplace transform of? Inverse Laplace transform of 1 over s plus 7. What did you say? Did you memorize? Sorry. Did you memorize this table by now? So if I have s plus 7, inverse Laplace transform of it is exponential of minus 7t, or if I had s minus 7, it will be exponential of 7t, and so on. So this is exponential of minus 7t. Okay, next issue. How does this show up here? Remember that we have to take this function and delay it by these many seconds. So I'll have exponential of minus 7. It's no longer just t, rather it's t minus 6. What else? Part 2 of it is that there is a switch that's going to kill the signal before 6 seconds. So I need a switch that is effective at 6 seconds. It's off before 6, and after that it turns on. Okay, so that is answer to this problem. Make sure you do quite a few of these things to be absolutely sure of where do these pieces go. Let's try one more of these things. So let's ask, what is the inverse Laplace transform of? Let's this time I write say 6 exponential of minus 8 s over s to power of 4. Okay, once again, you go ahead and pause this thing. Well, of course, you need to look at the formula, so maybe I'll just show the little clip. Hopefully that helps you to concentrate. So what do? We set this thing aside. So we ask ourselves for the rest of it. Inverse Laplace transform of 6 over s to the 4. You remember what that one is? It came from some kind of a polynomial. Remember that? Let's go back. Where did we do the polynomials? Here, or down here. So polynomial t to the n is n factorial s to power of n plus 1. So the power here is less than 1 less than power of s. So over there I had s to power of 4, I guess. So this is going to be t cubed. 3 factorial is already taken care of by that factor of 6 I had over there. So I'm all set. So this was easy. This was just t cubed. We didn't even need to change anything. What is the exponential going to do for me? What should I write here? So I hope I'm not. What do I write? Should I just write t cubed? No, it's not just t cubed. You have to delay it by 8 seconds. So I'll have t minus 8 cube, and then I want to kill the left side of this, and that is what the switch is going to do. 8t is going to make sure up to 8 seconds everything dormant is going on, and then it's turned on and it shows up itself. Okay, so this was a simple introduction to step functions, some simple examples, and in the future examples we are going to incorporate this thing into our differential equations. So it's going to be a combination of everything we learn about ODEs plus these things, and we are going to focus on that. So again, one of the OneNote is misbehaving. One of the shining moments of Laplace transform comes in when we deal with discontinuous forcing functions. Discontinuous forcing functions are made out of these step functions. They imitate addition and subtraction of weights to a pan of a oscillating spring. With Laplace transform we can do these problems rather quickly. If you want to go to old style of solving it that way, we can do it, but the solution steps are rather clunky, and then we have to kind of repeat ourselves quite often, and this becomes a selling point of Laplace transform. Okay, until next time, good luck and God bless.